There's a lot of electricity down there. So this is chapter 5. I couldn't find hydraulic systems in the book, so I don't know what chapter this would be in. But what we're going to do is look at different the systems. So this is chapter 5 in our book. And first thing we'll look at, or first thing they cover in the book is compressors. Now we know what the compressor does. What does it do? Compresses air. And we do what we call positive displacement. What that means is, so these are the different compressors we'll look at. Reciprocating, which is by far the most popular out there. Rotary screw, sliding blade, impeller, liquid ring, diaphragm, centrifugal axial pump, compressor. Probably rotary, the biggest ones out there are the first 3, and then centrifugal. There's a lot of centrifugal compressors out there. A lot of your little air inflators and stuff that you buy to inflate your tires, those can be diaphragm. So displacement is the amount of fluid that moves through the device in 1 revolution. And in compressors, it's in 1 minute, cubic feet per minute, gallons per minute, right? So usually this is the way we give the flow. Positive displacement is a compressor in which the measured quantity of the gas is entrapped between spaces, and then they decrease the space. If they decrease the space, what's going to happen to the volume? The volume can decrease. The volume goes down, pressure goes up, right? Everybody okay? Displacement is measured in cubic inches per revolution per minute or cubic centimeters per minute. So cubic feet per minute, so that's what we're dealing with here. Of course, we know the difference between standard cubic feet per minute and actual cubic feet. We'll look at different, we have a single stage compressor. This is when we have 1 or more cylinder with the same bore. We have multi-stage compressors, and this is where we have at least 2 cylinders or multiple cylinders or multiple stages. And we take the compressed air out of 1 stage and we feed it into another stage. Everybody okay? And the more stages you have, the higher the pressure. We'll look at a single acting compressor. This is what most of your compressors are. Double acting compressors actually compresses on both sides of the reciprocating compressor on both sides. Intercooler. So when we compress this air, somehow we're going to have to cool it, right? And then aftercooler. So intercooler, this is what we use in multi-stages compressors, where we literally cool it between each stage. And then aftercooler would be a lot what most of your industrial compressors do. They actually have some type of chiller or some type of cooler out on the output of the compressor. These are all reciprocating compressors. Single acting, double acting, single stage, and multi-stage. So this is a reciprocating compressor. So all we're doing is we have some type of prime mover that's turning a crankshaft, right? One thing. The crankshaft makes the pistons move up and down. When they move up, they decrease the volume. If the volume goes down, the pressure goes up. According to Boyle's law, yeah, if the volume goes down, the pressure goes up. Everybody understand that? And this would be multiple cylinders. Single acting, single stage compressor. So single acting, single stage compressor. This would be, we only have 1 cylinder in there. Most of your residential commercial compressors use this, 1 cylinder in there. And then we have single acting, multi-stage. I think there's a video here. Oops. So this would be single acting. What single acting means we only use one side of the cylinder to compress. One side of the piston to compress. Double acting means we're going to compress on one. Both sides. Everybody understand that? So my compressor at home is a single acting compressor, single stage, single acting compressor. This would be two piston. That would be the video I showed you. This is a double acting single stage compressor. So you notice on the double acting, what do? It compresses on both strokes, right? See that? Now what we do on stages, I don't know if y'all can see this on this diagram or not. So we take two or more cylinders, and then we take the output of one and we feed it into a smaller cylinder. So the second cylinder's got to be smaller, because if it was the same size, the air would uncompress when it goes in there, right? So you can tell these multi-stage compressors because each cylinder gets smaller. So we start off with a big cylinder, we compress it, and then the output of that goes into a smaller cylinder. And then we do what? Then we compress that. And then we might take it into another cylinder. The most I've ever seen on reciprocating compressors is 3 stages. And we can get up to over 200 psi with 3 stages. These are just the part. By the way, this is in the cylinder. You can see this. What we need to do, of course, is we need to, so you've got multi-stage compressors. They will always have an intercooler. What's an intercooler? That's a cooler between stages. Of course, here they're sending it through a pipe, and then the pipe has a bunch of cooling fins on every cooler. Right? Sometimes you'll see they'll do it a lot like the air conditioner, where they have a fan blowing through the vane to have cooling. A lot of your multi-stage compressors, you'll see they'll all have intercoolers between them. And then a lot of them will have an aftercooler. This is a typical 2-stage compressor. So you can tell, and normally on a reciprocating compressor, both of your stages are driven by a common family or common prime mover. Now this is the inner chiller. Of course, they're blowing it. This is the motor for the chiller. This is not also for the compressor. You can see this cylinder right here. This would be your input, and this right here would be your output cylinder. Can you see they're different sizes? So if you look at one and you can see the cylinder and they're the same size, it just means it's they get a bigger flow right here. And you see they drop the size down, and that's what they're doing. They're doing this to increase the pressure. Make sense? Okay. So
go back to that one. Is that one? My boss has one.
Yeah, this is a 2-stage compressor.
It's got that like radiator type thing.
Yeah, that's the intercooler. Right. And it's between stages. So we need to chill the air between stages, right? Or cool it down before we compress it. The temperature and compression is also, I forgot to do all that, but when heat things heat up, the pressure changes, right? So what we do is between the stages, we chill them. Now, if we looked at these and the cylinders were the same size, they're not using it to increase pressure, they're using it to increase flow. So what we do is each one of them will be working on, they might be working on, but if you look at them and they're different sizes, and they're not increasing flow, they're increasing pressure. So what they're doing is they're taking something that's already pressurized and they want to pressurize it more. So you're not going to fill it into a cylinder that's the same size, because as soon as you did it, it was uncompressed, right? Before you started, you ended up with one. So this is a three-stage compressor. So you can see this guy here inputs on the right, and then each time it goes through another stage, the cylinder gets smaller and smaller because it's taking compressed air and compressing it up. And you can tell these right off the bat. It gets a pretty high pressure out of these. So this is a multi-stage compressor. I can't tell how many stages it's got. Looks like it's got 2 or 3 on this side, and then it may have multiple stages on that side. So I don't know. These guys might be running in parallel. It looks like they might. So they might be doing this to increase the pressure and also the flow. So you got all types of compressors, right? You understand? Single action compressors, double action compressors, single stage compressors, multi stage compressors. And so what we do every time we go through a stage, we just take what's already been reduced and just reduce it further, right? This is a sliding vane compressor. This can be single. Can you see how this thing works? Can you see how it decreases the volume? Well, what happens, it's got these vanes in there, and they're all spring-loaded. You can't really see it. And this guy right here turns. It pulls in the pressure. It pulls in the pressure inside one of the big gaps, and as it moves around, what does it do automatically? It decreases the volume. If it decreases the volume, what happens to the pressure? Yeah, it's got to go up, right? So we said volume.
That's similar to the offset.
Yeah, offset is similar to a motor. So we have a vane motor. So what you're going to find out, a lot of your pumps and your compressors basically use the same technique that our motors use. So I can have a reciprocating fluid power motor. And I knew a guy that made a compressor. He doesn't know lawnmower. He literally made a compressor out of it. So instead of the engine turning, he brought in a prime mover on the drive shaft, and on the intake it would come in, and when it exhausted, it did what? It went into a tank. So it was really cool. So he basically just took an old reciprocating lawnmower and turned it into a compressor. So I'm going backwards there. A rotary screw. So on a rotary screw, what you do is you have 2 screws, and notice they're meshed together. And what happens is the intake on one side, and then they decrease the volume as it goes through the compressor. What's nice about a rotary screw compressor is it can give you a continuous flow without going through the tank. Are we okay? I can do this without pausing. No, hold on.
Rotary screw compressors are also positive displacement machines. These compressors employ 2 rotating, interleaved helical screws, which capture air in a pocket between them. The space in which the air is trapped becomes smaller as it moves down the axis of the screw. The compressed air is discharged from the opposite end of the intake. Rotating screw compressors can be used in applications ranging from 3 horsepower to over 500 horsepower. They are commonly used by roadside repair crews to power air tools and are also used for automobile engine superchargers.
So you notice those compressors that they use on the when they're out digging up roads, they don't have room for a water, big old tank. So they use a rotary screw compressor. It generates a lot of pressure, but you don't have to store it, right? Most of your reciprocating compressors, what do we have to do with those? We have to store it in a tank. And if we didn't do it in a tank, then what would happen is our air would do what? It wouldn't be a smooth flow. Your air would be, because you only generate, would only generate air on the compression stroke of your piston. And so what would happen, it would jerk. So normally what we do to compensate for that, of course, is we take the output of the reciprocating compressor and we put it in a tank. So your tank is only doing the pulsing, and then you get a pretty good even flow coming out of your tank. So these guys, they haul these things around on these little old carts in the back, hook it up on the back of their truck, and you say, well, there's no way in the world that thing's going to have a big old tank in it, right? And so it's a reciprocating screw. A rotary screw. Go ahead.
What the paint on? Paint struck and they same thing.
Oh, they do. Yeah, I guess they do. Makes sense to me. I think a lot of times though, they just pump the thing out. They don't. Liquid ring with the diaphragm compressor. Like I said, a lot of your little compressors that you buy to inflate your tire, stuff like that, they don't run a tank. A lot of times, if you ever pick one of those things apart, you get a diaphragm. So what they'll do is they'll have a vibrator or something that pulls the diaphragm out and causes air and pushes it back in. Of course, we have these check valves, right? So we have a check valve that's on the input that allows air to flow into the cylinder, and then we have a check valve on the other one that's found in the opposite direction that is exhaust. So all your compressors, your reciprocating compressors, are going to have check valves on them. Actual flow compressors, these guys work on work just like a jet engine. But you can actually see the spacing between the blades. You can see it real, so we start off with real big blades, and as it moves through the actual compressor, the blades actually get smaller and they get closer together. And there's more of them. So what they're doing is they're actually doing what? Decreasing the volume, which causes, if we decrease the volume, what happens to the pressure? So these are called actual flow compressors. Impellers. These are impeller or centrifugal compressors. So basically, what it does is it comes in here and it pulls air in, and then it narrows when it comes out, and then it shoots out the center. And then what they do is they cool it down, and then they'll run it into multiple stages. So most of your centrifugal compressors are definitely multiple stages, maybe up to seven stages that this thing will go through. And each stage, each one of these, they would get closer together, right? You understand? So these are centrifugal compressors. 5 to 50,000 cubic feet per minute. And this is a multi-stage centrifugal compressor. So basically, you just take the output of one and do what? Yeah. This is another picture of a big centrifugal compressor. Huh? You're going to use these guys if you need extremely high flow rate and you need smooth flow. Right? So you're not using a jumpy flow, you're using a real smooth flow at extremely high flow rate.
So
turbines would do the same thing. This guy here would be probably a lot easier to maintain.
So they use what, on chips and things like that?
Anything that requires a lot of air and a lot of flow. So like, that's usually water jets. Those are not. A lot of your ships now are going to the propellers actually move. So they actually cause the ship to go sideways on most of your newer ships. These guys are used in applications where you need extremely high flow rate especially if you got a bunch of stuff being used at the same time. And you got to imagine that it's, like in a parallel, your current divides, so your flow is going to divide every path that you go. So you might you have a real high flow rate coming out of your compressor, and then it divides out and goes out to different places. So I'm not really sure where they would use compressors out of US Steel. I know at US Steel they use a lot of steam, which is exactly the same principle. What's nice about steam is you don't have, all you gotta have is a boiler to generate, to cause it to pressure. Yeah, they use a lot of steam. I guess they still do. And of course, how fast the water would boil would determine the flow rate, and then take that and divide it out. Well, this got to get so many cubic feet per minute. So, if you're putting 100 cubic feet per minute, and this guy spit it off this guy, he might get 50, well, this other guy's only going to get 50. So, get into these real high demands for air pressure. Like, I don't know what they use at Bridgestone Power Plant. They use air all over the place. But then you got the main compressor, if they use one, it wouldn't surprise me if they use multiple. Would have to have an extremely high flow rate to support all those different machines that need to use that flow, right? That makes sense? We brought this up. This is called a scroll compressor, and it says I have a video, but I didn't put a link. So let me look real quick. This is what most of your air conditioners use. Your compressor inside your air compressor. Can you see how it works? So what it was, it's a real cute video. So for some reason, I didn't link that. This is a centrifugal compressor. And you can see this guy's got how many stages when it pops back in there? 1, 2, 3, 4, 5. It looks like it's got 6 stages of compression. So basically, you got one that feeds the other, which feeds the other, which feeds the other, right? And basically, what does it do? It sucks the air in on the center, and then when it's spinning, what happens? It just pushes it out. And if we change the volume when it starts going out, then it's going to pressurize it, right? I don't see my rotary screw, everything. I don't see my scroll compressor video. I don't know where I got it at, guys. What happens, this thing right here spins on the inside. It comes up here and takes it. And then, of course, the air moves through there, and then it just does what with it? I'm sorry. This guy wobbles. So if you ever did any HVAC or air conditioning work, you've probably seen these compressors. The problem is you've got an electric motor in there and everything's all sealed up. But then the I don't know if it's going to show us the. Well, this is the scroll compressor. You see it brings air in here, and as it moves around, what's it constantly doing? It's decreasing the volume. If it decreases the volume, the pressure goes up. So this is mostly your air conditioning compressors use a scroll compressor. Well, when we compress it, it gets hot. So what's the first thing they do? They run it through what they call a condenser, I believe. It takes away the, right? And then they run it through an evaporator, which causes it to go from a liquid to a gas. And when it goes from a liquid to gas, it gets extremely cold. And they send that to the evaporator, and then they bring it back and do what? Compress it. If you ever notice, it's got different sizes of piping, even on your car. You can tell the return size because it's big and the pressure size is small. You can tell that on your air conditioning too. So if you ever put Freon in your car, make sure you put it on the low pressure side. The other side's in there so you can hook up your gauges so you can look at your pressure differential. That's what you do. You fill it up for a certain differential between the input pressure and the output pressure. But always put your Freon in on the low pressure side. It's real easy because it's the water. The big one, yeah. Yeah, you hook it up on the high pressure side. What could it do? Blow up on you. So this is the scroll compressor. And all these are what we refer to as a positive displacement. And what do we mean by positive displacement? It inputs air and then does what with it? It creates this sign. These are our symbols. So notice the only difference between a pump and a compressor is the direction of it.
In commercial and industrial refrigeration systems, requirements for food safety, fail-safe product protection, low maintenance and reduced energy consumption, product protection, low maintenance and reduced energy consumption.
But that's okay. It was nice without video. So notice the difference between compressors and motors. So motors, the air is pointing in. From your compressors and your pump, so the air is pointing out, right? If we got air pointing out on the bottom and the top, what does it mean? It's bidirectional, so it's actually vertical. If we have an arrow going through it, what does that mean? It's variable. Everybody okay? Hydraulics, the arrowhead is colored in. Pneumatics, the arrowhead is what? Open. Very little differences between hydraulic and pneumatic symbols. And of course, we use this a lot to represent the whole flow, right? By the way, this on the side, this is where your prime mover would attach over here.
What would attach?
Your prime mover. So compressors and pumps have to have a prime mover. Something's got to move, right? Something's got to make a move. Two predominant methods, of course, is through combustion engine or through electric motor. So our compressors over here have electric motors. You get out there and you see crews out on the road or something digging up concrete and stuff like that with those jackhammers. Those guys are running off of compressed. So this is owner's manual for a oil lubricated air compressor. And these are what we're looking at. So this is SCFM. What's this? Standard cubic feet per minute. This is what they guarantee that the compressor, the flow rate that the compressor would give you at sea level, right? You understand? Actual cubic feet would either have to be measured, right? Or you'll have to look it up on the table and you'd have to know your elevation, how high it was. Now notice the next thing they give it is they give it at different PSIs. So notice at 40 PSI, we got 3 different models. Let's just look at the model 70 on the left. It could give us 3.8 at 40 PSI, and 90 PSI, notice it goes what? The flow rate goes down. Cut in pressure, cut out pressure. So this compressor would maintain, inside its tank, it would maintain a pressure between 130 and 100 PSI. So what would you operate your air tools at? Well, not 90 because it's going to cut in at 100. So on this one, you were going to, well, you're right. I'm sorry. 90, this would operate a 90 PSI tool, right? So what you want your tools that you get, you would want them to operate below the minimum pressure, right? Understand that. This is another one, air-cooled, tank-mounted with dry air filter. By the way, another thing you got to do on your compressor is make sure you filter that input air, right? Because if you don't filter it, what's going to happen? Well, it's going to clog everything up. All of these little valves, these little check valves and everything's going to get clogged up. It's just like running your car or your lawnmower without the air filter. Get that trash into your cylinder. Your cylinder start wearing out a lot faster. You start burning oil all the time because you let all this junk get into there. So filtering is very, very important. This says the mini series air cooled, tank mounted with air dry filter, cooler pipe, safety valve, pressure. But what we're looking at is, so this is not good. Why is this not good? Because here they only give me what? What does this say? CFM. What does that mean to me? What does it mean to me? What does that mean to me? It means nothing. Right, you understand? Because what's this relative to? I don't know. If it has an S in front of it, it's relative to sea level. Okay. If it just says this, it means nothing. Because this is going to be relative to some altitude, and I have no idea what altitude it is. Of course, here they give cubic feet per minute, and they give it liters per minute. But here but we don't know what that cubic feet per minute is relative to. Unless I could see what this note right here says. It might tell us something. Normal effective pressure for these different cylinders. Actual free air delivery. Cubic feet per minute. So what does this mean? Cubic feet per minute. Guarantee associated with this right here. And then there's an asterisk beside it. So I don't know exactly, I would have to see the asterisk to know exactly what that means. Not unless it's got some type of system that actually delivers that no matter what altitude you're at. This is my compressor I have at home. I got a Craftsman compressor. Now, this is the rating on mine. So the one I've got, will give me what? Standard cubic feet per minute at 40 PSI. Guarantees what? 5.1 cubic feet per minute at 40 psi, and it guarantees 3.8 at 9. Like that. But that's at sea level. So on my compressor, the only way I would figure out is, first of all, if I knew my altitude where I lived at, or the basic altitude, I could probably figure that out. The only other method we got is to have a flow control. And unfortunately, when they bought the pneumatic trainers, that's one of the things that they didn't give us. They didn't give us a flow control. What the cubic feet per minute on this compressor is, I have no idea. First of all, we'd have to find the compressor, right? As gases are compressed, they generate pressure, they generate heat. So we can do air cooling or we can do liquid cooling. Intercooler, what's intercooling? This is cooling between stages of a multi-stage compressor. After cooling is cooling at the compressor discharge point. What's that? Oh yeah. Yeah, but the problem is when you supercharge it, it does what? It heats up. Well, if you're going through multiple stages, what you're doing is you cool between stages, but then you got to do something on that final stage when it comes out that final stage. So the after cooler is always on the output of the compressor. The intercooler is going to be between the stages of a multi-stage compressor. Filters, intake filters, everybody okay on those? And a lot of problems I've seen people run lawnmowers without their air filter gets stopped up and it don't run right, and what they'll do, take it off. And then the thing runs maybe a couple more years and it starts using so much oil it can't use it anymore. Yeah. This is an aftercooler. These are using water, or chilled water. So what they do is they actually have inlet valves for chilled water, and then they shoot the air through this thing, and then of course it chills it down. Of course, receiver, but just about everybody, the technical name for these things are receivers, but just about everybody calls it a water tank. In fluid power and hydraulics, the technical name for the tank is the reservoir. But just about everybody calls that a water tank. By the way, why do they need to be, so in hydraulics we use, most of your reservoirs are rectangular. They're rectangular. But when you get into compressors, everything around it, even the ends. Well, air, if we push in the same direction, so if we push in the same direction, then your forces add together. If we push at an angle, then you get what we call the vectored sum of the pressure. So what happens, depending on the angle of the two, would depend on what actually sidewall pressure that the actual tank is. So if it was flat, then that 90 psi would be pushing against this area up here, right? You understand, this flat area. Right. But if everything's rounded like this, then all of a sudden they're pushing it all. They're pushing at different angles. They're not pushing in the same direction. They're pushing at different angles. So that means our walls can be a lot thinner. In hydraulics, though, there's no pressure in the reservoir. So they use a big old square reservoir using the bottom of it. But all your pneumatic reservoirs or receivers are going to have to be circular like this. Pneumatic tubing. What's nice about pneumatics is we use a lot of plastics in our tubing, which means the insulation. One big advantage of pneumatics over hydraulics is that the system itself is very, relative to hydraulics, it's really right. One big advantage, though, pneumatics cost you more to operate than hydraulics, because of the inefficiency of the pneumatic system. But another big advantage of pneumatics, of course, is it's fairly safe, right? So in hydraulics, most of the time the fluid is going to be an oil, basically. And you can't keep them things from moving. I don't know if you've ever been in a hydraulic room. You know, there's dirt all over the place because you get a hydraulic fluid to get out, and it attracts dust, and there's dirt all over the place. You know. Plus it's dangerous, huh?
Why does it go up to attract?
Well, they don't really attract it; it just retains it once it hits them. Well, anytime you put something in motion, it's probably going to get charged to it anyway. But look at the fittings, like on our fittings over there. A lot of our fittings are quick disconnect fittings. So you can just push them in, push them out, right? We use a lot less pressures. The systems are easier to maintain. Leaks are not good because if we have a leak, then of course we're going to lose pressure, but it's not going to hurt anybody. This is a typical piping system for pneumatics. We could basically do different sizes. So notice, of course, the outside pipes is handling your main flow. They'll be bigger because they got to handle a lot of flow. It's just like the water system is tight. Start off with quarter-inch pipes, and when you get down to the sink and stuff, you drop it down to half-inch pipes, right?
With the hydraulic, I know hydraulic.
Well, hydraulics does too. Anytime we go through something, we're going to have a pressure loss. But usually it's just like in electricity. Anytime when we play around with electricity, we say that our conductors, for calculations, we say it drops no pressure or no voltage, but that's not true. Everything has a little pressure loss. And of course, what determines how much pressure loss you get in a pipe would be what's on that inside surface and also the bigness of the pipe, right? And so the bigger the pipe, the less pressure we lost when you start getting flow. So you don't get pressure loss if you don't have flow. Y'all understand that? So y'all probably saw that over there on your meter. So you're sitting there and you're reading 60 psi. But as soon as you get flow, what is your flow? Yeah, drop. Because as soon as you have flow, so to have a pressure loss, you gotta have movement. And that's when we start getting pressure loss. So my valve, if there's no motion, if there's no flow, then pressure in and pressure out of the valve would be equal to each other. But as soon as you have flow, when you look at your output pressure on the valve, will be slightly less than your input pressure. And that's what the CD rating of the valve tells us. It tells us the pressure drop across the valve at a certain area and a certain flow, right? That makes sense? So notice the closer we get to the device, the flow is going down. So at the top pipe, we got all the flow. So that top pipe up there is supporting the flow of everything in the system. And when we start branching out, then the pipes can start getting smaller because the flow is divided out among the system. Well, no, it's to reduce the cost of the system. It's just like if you go out there at Lowe's and you look at an 8-foot section of quarter-inch pipe, it's going to be a lot more than an 8-foot section of a half-inch pipe. Right? You understand? So the less flow that we're going to have, then what do we start doing? We start making it smaller piping to decrease the cost. It's just like we tell people, they can come into your house and they can run 8-inch wires all through your house. Be very, very expensive, but it'll handle 15 amps without any problem. But then you wouldn't be able to buy outlets for it too. So the hydraulics, I couldn't find a section in the books that talked about a hydraulic system, but what does the pneumatic system consist of? First of all, it consists of a compressor, a prime mover that moves the compressor. You got to move the compressor. Then depending on what type of compressor it is, it may or may not require a receiver, right? You understand, or a tank. Most of the compressors that we see has a tank out there to store the pressure. Then we have what? Well, the compressor might have coolers on it. They all have coolers. It's just most commercial compressors or residential compressors, your cylinders are going to have a lot of vanes on it, right? Kind of like, not on your car, but kind of like on a motorcycle, where they have the fins up there. And then it might run it through some type of radiator. What do we need on a hydraulic system, though? We're going to have to have a prime mover, right? You understand? We're going to have what? We're going to have a reservoir. Okay, then what we're going to have? We're going to have a pump, right? What else do we do? Maybe, could be, possibly, most of the time we have some type of pressure relief valve. So in pneumatics, we use a pressure regulator. In hydraulics, we use a pressure relief valve, right? So the pressure relief valve just sends it back. Any pressure that tries to get above a certain level, it just sends it back in time. We're going to have, in both of them, we left it out, we're going to have piping. We're going to have some type of control mechanism, right? Control the direction of the flow. So we got to have directional control valve, and then we got to have some type of actuator, right? So on a hydraulic system, we still have a prime mover, then we have a watt, then we have a reservoir, then we have what? Got a pump, got piping, directional control. Got a pressure relief valve. The pressure relief valve is all is going to be right by the compressor. I mean, not the compressor, right by it's going to be on the tank, right? Does that make sense? And we're going to have some type of actuator, right? Okay. And we're going to have filters. We got to have filters. Reservoir holds sufficient liquid to meet the system's demand, acts as a heat exchanger, acts as a fluid conditioner. So what fluid conditioner, anytime it comes back, it falls back into the tank. A lot of times it creates bubbles, and we have to have some way to make sure we don't get any air bubbles in the system, right? Because fluids are basically considered to be, liquids are considered to be uncompressible. They do compress a little bit, but it's beyond our understanding. And if you get air in there, then air is compressible. So that creates a lot of problems. Anybody that had to bleed brakes in a car understands that. Some way to get rid of the heat. The reservoir should hold 2 to 3 times the pump's output per minute, ensure a high enough fluid level that when the actuators are extended, when all the actuators are extended, there's no whirlpool that affects the pump suction of the pump. So just like in your bathtub, when you start draining your bathtub, you don't see a whirlpool. The closer it gets to the drain, it starts spinning. And what's that doing? That's sucking air into the system. So you want to make sure you always have enough air so when that pump is pulling it out from the bottom, it's going to come up from the bottom, that when all your actuators are fully extended, there's still enough fluid in there to keep that pump from creating a whirlpool, because if it creates a whirlpool, it's going to put a lot in air, which is not good. Enough air, have enough airspace when all actuators are fully retracted to allow for thermal expansion. So this is going to determine the size of your tank. So if all your cylinders are retracted, so when you extend all of them, they create a whirlpool. When you retract them all, you fill it up so it don't do that, and you retract them, and your tank overflows, right? So it's going to be somewhere in between that. Tall and narrowable is preferable to wide and flat. Parts, we have a oil level indicator. inside the reservoir. You need to know what the oil level is. This is usually nothing but a sight tube on the side. So we'll have a glass tube on the side that can show you right off the bat. You need to have some way that you can feel it when it's low, right? You need to have some way that this breather, what do you mean by breather? Where it can keep the pressure equalized. Because when it starts dropping down, the pressure, you can have some type of breather, so the tank can breathe. It's just like a fuel tank in the car. It's got some type of breather on it, right? Internal access doors, baffles, water baffles. That's just usually holes and stuff like that causes the fluid to flow even, not slosh around. Anybody that was in the waterbed, anybody got a waterbed? Yeah, we used to have one too. What they call a free flow waterbed. It had no baffles in it, so you get on that thing. Because there was no baffles, but then they came in and they put the dividers in there that had a bunch of holes in there, and you lay on them and it would be foam. Got to have a drain plug, so the baffles keep the fluid from doing what? Flopping around in there. A drain plug, usually have a temperature gauge and some type of filter. Are we okay? So this is a typical reservoir. Of course, the reservoir would be down on the bottom. And I don't know if we got a picture of what makes up a reservoir or not. So usually it'll have baffling in it, and it'll be a square, and then you'll have a baffling in the center. Your pump is going to be up in here or onto the side somewhere. And then what it's going to do is we want it to do what? Create suction on this side and then shoot it down toward the bottom. Then your return will come in here. Now sometimes they do this a different. Normally they'll come over here and drop this through a filter. And then, of course, it's going to fill it up in here. And then it'll drain in. Of course, it creates bubbles. And so that's why over here we do what? We have a baffle, right? So the bubbles can't get from this side over to this side. And it draws a level. So this is a typical tank. Now, so the bubbles will be riding on the top. They can't get across anyway because of the baffle. So this baffle over here, this is and as long as we don't create a suction tube over here when it's trying to suck, then we're not going to get bubbles in there anyway. So if you ever looked on a brake cylinder on a car, you notice that the output is down at the bottom. Where's my PowerPoint? Your hydraulic piping is going to be a heck of a lot more expensive. And why is that? Huh? Yeah, there's going to be high pressure. So one big advantage, by the way, we don't need my glasses. Okay. That's my train of thought. You don't want to do that. So a hydraulic system is a lot more expensive to install than a pneumatic system because our piping has got to maintain that high pressure, right? I mean, we use a lot of steel piping, metal piping in hydraulics. The only time we try to use flexible pipes is when we're going from something stationary to something that's vibrant. So even on your car, if you look at your air conditioning system, the only flexible pipe is the one that goes from the compressor, which is out on your engine, and then it comes over to the metal pipe, and from then on, it's all metal pipe, right? So the system itself is a lot more expensive. Your coupling is going to be a lot more expensive. Everything in the system is going to be a lot more expensive. And not only do we got to take the fluid out, we got to do what? We got to bring it back in. So on our pneumatic system, we don't have to bring it all the way back to the reservoir, because what's the reservoir of the pneumatic system? We're in the reservoir for most pneumatic systems, right, that use air. And air is the predominant gas that we use.
A lot of different kinds of things too. Out of the day. Like,
Yeah, you don't see very many, even in a laboratory environment. So our hydraulics lab had quick disconnect feeding, and they were a lot like the feedings that you get for your compressor. Most people have a compressor have that quick disconnect on them. The problem that we had is we had to do that because we were in a lab environment and we had to hook up different circuits. And what you did your piping on, you did your piping with those quick disconnects. Well, what would happen every time you pop one of those quick disconnects open, some of it, even though it had a check valve on it, it still had pressure. So we ended up with hydraulic fluid all over the place. You're not going to see hardly any quick disconnects out in a hydraulic system. It's always going to be screwed together. You know, everything's going to be screwed together. Everything's going to be bolted down really nice. So your high pressure tubing is very expensive. I don't know if anybody's ever had to change the high pressure tube out on the air conditioner on your car. Be ready. Those things are very expensive because they're reinforced. You know, they got all type of layers. They'll be real round, but if you ever, the inside is really little. They got all kind of layers in it. They'll keep the pressure in, not the cold in, the pressure in. Your compressor never, I mean, your compressor doesn't see cold. It just sees what it gets back, right? Where does the cold come from? Well, the cold comes, so when they run through the compressor, it takes a gas, it puts it under so much pressure, it takes a gas and converts it into a liquid. And that's one thing, the problem we have with gas is in extremely high pressure, because the more pressure you put a gas in, sooner or later it's going to try to go to change into a liquid. So your compressor doesn't see, your air conditioner, it does not see, it sees a gas, right? And then it takes that gas and converts it into a liquid. So we got a thing out there called an evaporator, which has a little, I forgot what they call it, a little squirt gun in there. But it squirts it out and converts it back into a gas. And when it goes through that conversion process from a liquid to a gas, it gets extremely cold. It's just like even hairspray. You know, you spray that stuff on your hand, it's cold because it's going from a liquid to a gas, right? So when we go from a gas to a liquid, when we pressurize it, the temperature goes up. When we unpressurize it, it goes down. I do that all the time. I'll take my compressor, got a little squirt thing on, I'm real hot. I'll blow that thing under me, and when it comes out and goes back when it comes back and spreads out, it releases heat. Or absorbs heat, excuse me. So your compressor's not seeing, it's not seeing the gas, it's not seeing, the temperature. It creates temperature. It gets hot when we compress it, right? So the pipes are not in there to keep the temperature in, it's in there to keep the pressure in. So pumps and motors, we've already looked at these, right? Vane, outside gear, piston motor, we've already looked at this. Accumulator. So accumulator, we don't have accumulators in pneumatics. We have accumulators in fluid power. So this is a good time. Let's stop and take a break right here. So all your notice your motors can also be used for pumps. We talked about even the guy that made a compressor out of his lawnmower. So we have the position, we have the outside gear, we have inside gears, the accumulator. Now the problem, one feature that we get from a pneumatic system that has a receiver is that if power fails, we got that big tank out there charged up. we're going to maintain pressure, right? So this is extremely important. Things that are moving things around using fluid power. Because when power fails, if you lose that pressure source, you've already lost the pressure source of the electricity, right? If you lose that other pressure source, then things are going to fall, things are going to drop, something happen. So the problem with on hydraulics, so pneumatics, what we have to do is we have to pressurize it before we use it. Fluid power creates pressure when you use it. So the problem is, if I've got a hydraulic system out there and the power fails, then I lose all my flow. As soon as I lose all my flow, I've lost all my pressure. And that could cause things to drop, things to move, things to happen, right? You know what I'm saying? So they had to come up with some method to maintain hydraulic pressure even though the pump wasn't spinning. So they came up with something they call an accumulator. An accumulator is just a big old tank. It's usually vertical. And then they do something. They either use big springs in there, and when the hydraulic pressure is going, the pressure pushes the spring up, and if the prime mover ever goes off, then it gets pressure from the spring. They use bellows. They use inflated bellows. They use big old weights. There's different ways they can set up an accumulator. An accumulator is nothing but a device that maintains hydraulic pressure even though your pump's on. So a lot of your big industrial complexes will have them. Because most of these guys cannot afford an unorderly shutdown. Now, of course, if you do use electric power, it gives them the ability to orderly shut down, right? To set something down that's being picked up, to move things out of the way. But they got to have time. Of course, these accumulators, it's just like a tank. It's just like a tank on your compressor. If your compressor stops, eventually that pressure is going to bleed off, right? You understand? But you do have time to do what? To put things in order. So that's all an accumulator does. We weighted vertical cylinders with a weight acting against the rod will maintain a constant pressure over a range of operations. Plus, what's nice, another feature of an accumulator is an accumulator will move out the flow. So if there's any jerk in anything inside your flow, when the actuator moves or something, the accumulator will absorb that shock. Yeah, we put these things on my sister's house. When she'd turn on one of her things, the pipes would hum. It would hum like that. It was really strange. And what did? Well, they just came up there, they cut it open, soldered, put a big old jug on the side of it. Just that's all it was, a jug, and all it was an accumulator. Same thing. So even though the fluid over here was vibrating when it hit that accumulator, what did the accumulator do? Well, it absorbed it. So when it tried to drop the pressure off a little bit, the accumulator fed. When the pressure went back up, the accumulator would recharge. So accumulator, we use accumulators to even the flow of the hydraulic fluid. So even though you're out there jerking these things around and moving stuff and getting more flow, no flow, this guy has a tendency to maintain a constant pressure, even though we're trying to get pressure drop in our system, right? And plus, they give us a pressure even when the power fails over a limited time. We'll maintain a constant pressure over a range of operations. So these are just examples of accumulators. They're usually big old cylinders, and then somehow they got something in there that does what? They keep the fluid pressure up. So they use big old weights, they use springs, they use bellows where they inflate them up with air. I've seen them with air. Yeah. So 6 days of operation accumulators is empty, no gas, and this is just showing you how they work, which is basically pretty obvious on how they work. Are we okay? Relative output, 10 gallons accumulator, system pressure. So see, these are compression ratio. This tells you different things about it. This looks like these are bladder compressors. That would be this one on the top. So it's got a big old bladder in there. It's usually full with, not with a liquid because it's uncompressible. So it'd be some type of gas, right? The hydraulic fluid comes in on the bottom. starts decreasing the volume in the top, and starts decreasing the volume, what happens to the pressure? Volume goes down, pressure goes up, right? So these are all 10-gallon accumulators. Horizontal mounted accumulators can cause uneven bladder wear and trap fluid away from the hydraulic valve. So very seldom are you going to see an accumulator that's mounted on the side. It's going to be mounted on a cutaway view of a pressure gauge. Dang, guys, I didn't bring. We've got a ton of these over in the shop over there. A lot of your pressure gauges use what we call a Bourdon tube. A Bourdon tube, and we have a helical Bourdon and we have a C-shaped Bourdon tube. And this works very similar to the little, everybody played around with it when you was a kid. These party blowers, yeah. What happens on them, they have a spring in them. And when you put pressure in them, what did it do? They uncoil, right? You understand? And then when you took the pressure off, they do what? Coil back up. So if I take a chunk of metal and make it hollow, make it flat on the sides, and then I put pressure into that C, what's it going to do? It's going to do what? So it's in a C shape. What's it going to do? It's going to try to do what? It's going to try to straighten out. That's what a Bourdon tube is. We have a helical Bourdon tube, but the tube is actually a twist. And when you put pressure in it, it wants to do what? It wants to untwist. Here, these are very, very popular. And then we attach some type of movement on it. So you can see it right here. And then this causes the little, the indicator to move. So this is Bourdon, very, very popular. All this thing does is come in here, goes into the Bourdon tube. When pressure goes up, it causes the Bourdon tube to try to straighten out. We can use these on vacuums too. Except on a vacuum, it would try to make it tighten up, right? You understand? Pressure would cause it to do what? Straighten out. So we use these on pressure gauges. This is probably one of the most often used pressure gauge buttons. We use these in pneumatics. We use them in hydraulics. They work very well on both of them. Bellows gauge. I've got every one of these guys over in my shop over there. We use this in a class we have a class we call sensors. If you're in the AUT program, that'll be one of the classes you have to take. One of the things that we want to sense is pressure. That's very important to sense pressure. If you don't have enough pressure in the system, then you're not going to be able to create the work. If you get too much pressure in the system, then you're going to tear things up, right? To break the lines, you could press the seals on your actuator. You could cause things to explode. Yeah, I like those drag racers for some of those turbines.
You run too much pressure in the turbo, like turbo, too much turbo pressure.
Well, even if you got a weak component in it.
Yeah,
It's also you blow up. So this is Bourdon tube. This is a bellows. So bellows is nothing but these are usually made out of brass. So you can't see it, but they like this. And then one side usually mounts on a solid item. And then we put pressure in one side. And what's that going to cause the bellows to do? I messed up. Yeah, it's going to cause it to expand, right? Okay. And of course, depending on the material you made, usually we have this thing up against some type of calibrated spring. A calibrated spring is a spring that's made with such preciseness that it will compress and expand at a certain amount, a precise amount, depending on the pressure. If you ever go into a grocery store that has one of these rotating uses it over in fruit. It's got that basket on you, and people go in there and measure the fruit. That's usually the calibrate spring. That's how I actually those things off. So you go there and you try to stretch that thing out, and the more you stretch it out, the more force it creates, right? And then what happens is when the force equalizes, then that's where the corners come. So we have this thing on a calibrated spring, so when the thing expands, it'll expand a certain amount until the pressure equalizes. So this is another method that we can measure pressure. And of course, pressure is a flow meter. We don't have any flow meters, unfortunately. The flow meter, can you see how it works? So it's got a calibrated spring in there. And then we put pressure in, and then what is it going to do? It's going to start pushing against this thing, and it's going to start pushing until the force on the spring matches the force of the fluid, and then they're going to rotate that as flow, right? I don't know about that. Shock absorbers. We use shock absorbers. So over on our manufacturing line, we got several shock absorbers on the robots that move back and forth on the very end to keep it from banging up against the side. We do shock absorbers. Everybody know what a shock absorber does? Well, how does it do it? How does it do it? Could be fluid. What we do is we have an orifice. Yeah. Fluid, we push against, we cause the fluid to flow through an orifice to go over to the other side. And the size of the orifice is limit the size of the flow of the fluid, right? Then change the pressure. Heat exchangers. We're going to run into these, especially in fluid systems, pneumatic systems. We do this a lot. You'll see how this guy here works. Now this is pretty standard. Radiators, everybody's seen these guys, right? Well, what determines how much heat we get out is what the surface area. You're exactly right, but it's the surface area. How much area we have exposed to what we're trying to get rid of. Right? And then also what type of material does that heat go through. The best conductors of electricity are also your best conductors of heat. So silver would be the best conductor of heat because we don't use it. We use copper. We don't use much copper anymore, but you used to people with steel drain radiators out of your car. They were copper because copper is one of the best conductors of heat.
When did radiators?
Normally they use aluminum now.
What are they?
Aluminum is a good conductor of heat. It's not as good as copper.
Right. But when did they split?
Huh? Not as good as copper. Copper is better. Copper is better than it's ever in computers. You did stuff with we used to call it overclocking. You ran your computer, you ran it faster than what it was designed to run in. You know, and what you had to do is you looked at the difference between a copper heat sink and an aluminum heat sink. You'd see quite off the bat that the size was a lot different. Copper heat sinks are a lot smaller. Sometimes you get into a laptop computer, they still use copper because they're limited to what? Space. And they'll have a chunk of copper both on top of the processor, and then they'll run it through over to where the fan. So the fan is not copper. Well, the transmits heat better. So it has a very low resistance opposition path to heat. And once you get it, so when the formulas we use for heat transfer are exactly the same as we use in electronics for voltage. But here you have what they call thermal resistance. So copper has a lot lower thermal resistance than aluminum. It doesn't mean I can't dissipate the same heat. But the problem is that the heat, to get the same heat, an aluminum heat sink would have to be bigger than a copper heat sink. Okay, does that make sense? Because it's got more thermal resistance. So most of your radiators now, the fans and everything are aluminum. Yeah.
I wonder where this thing is like high performance, nobody ever goes for copper. That's very why. We did it everywhere, like aluminum.
Yeah, copper.
From my understanding, I say, like aluminum, just like copper.
Most things that might be.
I mean, like you had, like you go to, so it's like the same thing. One on copper, one on aluminum. It's gonna break with the copper.
Yeah, but we're talking about the transfer of heat.
Yeah.
So copper transfers heat from what it's transferring heat from to the outside. But one of the problems they use in race cars, because race cars, you're really cognitive of weight. And a copper will, even for the same resistance, does that make sense?
Yeah.
It could be smaller, but the smallness of it would not compensate for the weight. In a laptop, they're going to use copper in there because, well, it's still not that much copper too. So.
How do you determine that? How do you determine how much power?
What do you mean?
That calculation?
Yeah, there's a thermal resistance of copper at the bottom. So it just you would use the same technique that you would use to calculate how much voltage a wire would draw. So what you need to do is you need to know, huh? Yeah, but copper has a lower thermal resistance, but the mass is basically the same.
You use that math to say the size.
Yeah, so you could say, okay, you could swap that around and say, well, I need to get rid of this much heat, how much surface area then. So there's a lot of math involved with it. But what it is how much surface area you need to transfer as much heat as you possibly can. And then, of course, what we do on a lot of automobiles, we also force air through the radiator, right? To help increase the heat.
Aluminum block, you see that the computer there, there's one. Just put all of it.
You mean a motorcycle?
No, on the computer, there's home computer.
Oh yeah, the heat sink.
Yeah.
But if you look at the copper ones, they're going to, for the same thermal resistance, they'll be smaller, but they're going to cost a heck of a lot more.
They make a lot of difference.
And normally, when you bought an Intel processor, it would come with the heat sink. But if you were going to overclock it, then you had to use a different heat sink, because that heat sink that was on there was designed for that processor running at its greatest speed. Yeah, they're all of them. In desktop computers, I've never seen unless you buy one of these big high dollar. All of mine, I use aluminum. So I don't know if it's yeah, a lot of your laptops use some type of liquid that it cools, and it usually uses the flow that's caused by heat. Heat causes things to expand, which would cause things to go in motion. So that's normally on those laptops. You'll see a tube going from your processor over to your. So that's it, guys. So we went through a different system. So what we have on a pneumatic system? What's the components of a pneumatic system? Yeah, but don't forget the prime mover. The compressor don't move by itself, right? So we're gonna have some type of prime mover. Combustion or even turbine, even our power companies use a lot of turbine to move the prime mover, to do the prime mover for their generator. So, but you got to have some type of prime mover. Predominantly in fluid systems, the main compressors that we use, prime movers are either electric or combustion. Those are the two guys. With electric by far being the largest majority. And why? Because electricity is everywhere. Right? Rather than
When they made it, back in the day, when they made it secret for that factory or it was like a single.
That's a really good question. And odds are, when things were first put out, and we don't have a lot of that anymore. Well, that's not true. Most of this stuff was made for specific manufacturers. But compressors have been out so long, and they've got so many variations and some of those are still made specific. So a company's if a company knows what flow it needs and what pressure it needs and all this kind of stuff, if it's not one available, then by George, somebody will be able to do what. Now that they don't make, so there's still a lot of specialized equipment out there. A lot. So what parts do we have to a pneumatic system? We have what? We have a prime mover, then we're going to have a what? We're going to have a compressor. Then normally we'll have a receiver, right? Or a tank. Then we'll have our what? Piping. Then we'll have our control valve. We don't run an actuator while it's control valve, normally. Then we're gonna have some type of actuator. What other might we have? But this is what we're gonna have. What else might be? Of course, we gotta have what? We gotta have filters, right? We're gonna have some probably have a pressure regulator on the pneumatic system, right? Not necessarily, but right, odds are. What else are we gonna have? We might have coolers, right? Right, are you okay? What do we require for a hydraulic system? Gotta have a prime mover. Gotta have a tank. Gotta have a pump. Gotta have piping. Maybe, maybe not. Yeah. You understand? Pressure relief valve, a lot of times it's going to be there, but on a lot of systems, it's not required. So I've got a hydraulic system at home where I jack my car up. But I don't think there's a pressure relief system on that. That's a bleed valve. So then we got directional control valves. We have piping, but on a hydraulic system, we got not only do we have to have piping going out, we also got to have water coming back. Right? It'll be okay. All right. All right, guys. So y'all got any questions? Okay, so it's 12:16. That's only 45 minutes left in the class. So we only got 45 minutes allowed. So what we're going to do now, if you need help with me advising you about what you need to take for the spring. So what we're trying to do is we're trying to get everybody to go ahead and enroll in the spring semester. The classes that you know you need.
I ain't gonna be here. I'm gonna go.
I need to sign.
So if you're going to enter your own schedule and if you don't need any advising, this would be a good opportunity for you to go ahead and head out. If you need advising, I'm going to do that now, but this is the last time we'll do it for this class. Everybody understand? So after this, it won't say, I need to have another schedule. I'll say what.
I need to. We had a class period.
Yeah, we had class period. All right.
Before we go first, I just need 3 classes.